Okay, so let us get started. Today I want to talk about a very typical problem that you may encounter in your homework or exams. So it's called flows with lower bounds. As I said, this kind of problem, you'll probably encounter it in your homework or exam. So it is stated like this. Suppose we want to maximize a flow V subject to, so remember that V is some network flow. So the constraints are like sigma J So let us look at it. We want to maximize the flow V and subject to, so that's to say for each node I, we use the sum of the outflow of I minus the sum of the inflow of I. This equals to V if I equals to S. So that's to say this is your S, and the outflow of S should sum up to V, and for T, the sink node, all the inflow of T also sum up to V. But remember that so we use the outflow of I minus the inflow of I. So for S it is V, and for T it is minus V because we use the outflow minus the inflow, and for T the outflow is 0. And for all the other intermediate nodes, the outflow equals to the inflow. However, here, look at this. Xij is larger than, is not only less than or equal to Uij, but larger than or equal to Lij. And Lij here, we assume Lij is positive. Otherwise, you can just solve it by the max flow algorithm that you have learned in the lecture. So today we want to discuss about this class of problem. Then, when we are looking at this class of problems, a very natural thinking is this problem has two phases. Here I say two phases means that you can solve this problem stage-wisely. That's to say you first solve the first stage, and based on the first stage, you solve the second stage. So the two phases here are first, we want to ask the first question, does a feasible flow exist? So remember that for all the intermediate nodes, the inflow equals the outflow. But for the flow on each arc, it should be bounded by Lij and Uij. However, by designing Lij and Uij properly, it is possible that there's no such feasible flow. So for example, a very easy question. Node 1, node 2, node 3. And suppose the node 1, the lower bound is say 5, upper bound is 10. But for node 2, but for the arc from 2 to 3, say the lower bound is 1, the upper bound is 2. Then there's no feasible flow, right? This is very straightforward. So the second question is how to convert feasible flow to feasible max flow. So this is a common way of thinking in optimization problems. So we know that for optimization problems, if the objective function is very easy and straightforward, like what you have learned in middle school, like a parabola, then you know that you can just use the formula to calculate this point, right? However, if this function is very weird looking, then you need to use some algorithm such that you start from some point, which is a feasible point, and then you iteratively converge to the optimal point. So the second phase is that if suppose now I have given you a feasible flow, it is feasible. Then how can you convert this feasible flow to a feasible max flow? Basically, the second phase is easier, and the first phase is kind of harder because it is a little bit complicated. So I will discuss the second phase first. Or we discuss the second phase first because it is easier. The second phase, okay. Suppose we have feasible flow X in the network. So that's to say we have an arc, a node I to J, and the flow is Xij such that Lij less than equal to Xij less than equal to Uij. Okay. Then I give you 1 minute to think about it. Suppose we have a feasible flow on X. How can you transform it into a feasible max flow using the knowledge that you have learned in the max flow algorithm in class? Give you 1 minute to think about it. If you come up with an idea, just shout out. Any idea? So I'll give you a hint. The hint is that in the max flow algorithm, you are told to construct a residual network, right? So what does the residual network tell you? Anyone has an idea?
Tells us how much more we're able to say.
Okay. Half done. I can tell you that you are half done. Well, what is the so you need to decide how much more you can add onto the arc. What else? You can increase or can you decrease? Is it possible for you to decrease the flow on some arc so that the overall flow is increased? Is it possible? Actually, it is possible. Okay, so Thomas is almost correct. So just take this example. For each arc, okay, we know that in the residual network, in the max flow algorithm, suppose you have I and J, and originally you have an arc from I to J, right? And when you are constructing a residual network, you have I to J and another arc J to I. So I use the dashed line here. What does I to J? So in a residual network, what does I to J mean? It means that how much more you can add onto this arc, right? But J to I, in terms of the magnitude of the flow on J, in terms of the magnitude of J to I, it is equal to how much flow is already on the arc from I to J. So that's to say the arc J to I represents how much you can reduce from this arc Ij, right? How much flow you can reduce, because if it is possible that you reduce the flow on some arc, but in general, the overall flow becomes larger. How to do that? From S to T in the residual network, you use DFS to find a directed path. and then you increase some amount of flow on this arc, and the so-called amount is the minimum of the arc value on this path, right? So think about how to execute the max flow problem, the max flow algorithm. So this is the residual network. This is what the residual network tells us. Then for this problem, Xij is already greater than or equal to Lij and less than or equal to Uij. So that's to say, we can say that we can increase no more than Uij minus Xij on our arc I to j. Or we can reduce no more than Xij minus Lij on I to j, right? Because we need to, for feasible flow, we need to make sure that Xij is greater than or equal to Lij. So that's to say we can reduce at most Xij minus Lij from on the arc I to j. Then how can we construct? So then we need to construct the residual network. So this is equivalent to the max flow algorithm, but we are already in some intermediate step. But we need to continue so that finally we can get the optimal solution. So how can we construct the residual network? This is I, this is J, and because we can increase at the most Uij minus Xij, so this arc from I to J is Uij minus Xij, and the arc from J to I is Xij minus Lij. Clear? You can increase at the most this value, and you can decrease at most this value. And no matter you increase or decrease, one thing that we can make sure is that one thing that we can make sure is that the Xij is always in this range, and because we are already given a feasible flow X, so that's to say for all the intermediate nodes, it is balanced. The inflow equals the outflow. So this is equivalent to in a max flow algorithm, you are given an intermediate step and you need to continue to get the final result. So this is the way to convert a feasible flow to a max flow. So let me complete it. So we construct the residual network. Then what's the next step? We need to find a directed path from S to T in the residual network. Then suppose this is S, this is T. For some of the arc, it may be from like this, it is I to J. But for some of the arc, it can be this dashed line. That's the reversed arc, right? So suppose you have a path from S to T. Then how can you augment the flow on this path? So suppose the value, the minimum value on this directed path is say 1. Then you increase 1 unit flow through this path, and then you modify the residual network and continue. Right? This is the max flow algorithm that you have learned in class. Okay. And I remember this in your textbook. This is also called the shortest augmenting path, right? Have you heard of this terminology? Shortest augmenting path. Yeah, because you want to augment the flow through this directed path. So shortest augmenting path. Okay, so this is the second phase. Then we deal with another thing that is a little bit more complicated. So the first phase. So remember what is the first phase? The first phase is to find a feasible flow. So the first phase is to find a feasible flow. Also, I'll give you 1 minute to think about just a brainstorm. How can you find a feasible flow? So the hint is that you need to make some transformation for the network. You need to make some transformation to the network. So how can we find a feasible flow? All right, so it doesn't matter if you cannot figure it out. So, but I have to say that for a network like this, to find a feasible flow, the technique that I will introduce is a very common technique. So always keep in mind. Okay, so the idea is to transform into circulation problem. Have you heard of this terminology in class? Circulation problem. So a circulation problem is like on a network, but the flow, it should, as the name suggests, the flow just circulates along this network. So how to transform it into a circulation problem? A very easy way. Okay. This is your S, this is your T, and suppose these are the intermediate nodes and the arcs between them. Then to transform it into a circulation problem, we add an additional arc from T to S. As to say, we connect T to S. What is the capacity? With infinite capacity. Because we are maximizing V, but we don't know the upper bound of V. So definitely we need to set this arc to have infinite capacity. And that's to say XTS is less than or equal to infinite, positive infinity, but larger than or equal to 0. There's no positive lower bound and no need to set a positive lower bound. Right? Okay. So then how can we formulate a feasible, finding a feasible circulation problem? So a feasible circulation problem is to identify flow X such that minus so look at this difference. So we want to find so the problem finding a feasible circulation problem is to identify a flow X such that for any I in N. Now you see the difference. We are not excluding the nodes S or T because we have already connected T to S. That's to say the flow goes to T and then returns back to S. It's like a circulation. So now that's to say for any node I, the outflow equals the inflow. That's a balance. And Xij should be larger than or equal to Lij, or say bounded by Lij and Uij. So you see the difference. Then we have transformed it into this problem. what is where is our trouble now? What makes our problem solving become harder? What is our problem now? Our problem now comes from this, right? The lower bound, because we know that the lower bound is Lij is greater than 0 for I, j that is not from T to S. This guy brings trouble to us, and we need to eliminate the trouble brought, which is brought by this lower bound. So our next step is to eliminate the Lij. That's to say, we want to transform it into another problem such that this Lij is this lower bound is just a 0. Okay. Next, try to make lower bound be 0. How? My question is how? How to make this lower bound to be 0? So to intuitively explain this lower bound, so we know that in this circulation problem, this is just like an economy, right? Your boss pays you, and you want to purchase something. You pay the retailers, and we know that the money in an economy is circulating, right? However, we want to. So what does the lower bound tell us? The lower bound tells us that the lower bound, say from I to j, it tells us that I should prepay some amount of money to j, right? This is just like if you go to a restaurant, then they tell you that you should purchase the food at least say $20 or so. You know that there are some restaurants like this. They set a lower bound to the price of the food that you have purchased. So Lij, how to understand it? It is like prepaid or say set a minimum consumption. So how do we make this lower bound to be 0? The way is to introduce by introducing balance bi. So if you remember, in the week before last week, I mean, excluded the spring break, we talked about narrow transformations, right? So in the narrow transformations, there are some problems about the balance bi. That's to say, for a node I, the inflow not necessarily equal to the outflow, but equal to, or in other words, the balance is just the difference between the inflow minus the and the outflow, which is not necessarily equal to 0. So we introduce this balance bi, and what do we do it? We let xij equals to xij prime plus Lij. So this is just like you need to pay, I needs to pay xij to j. So that's to say, this is the lower bound, or say the minimum consumption, plus the premium that is paid from I to j. So we can interpret xij prime to be the premium that I pays j. Okay. So this here now, Lij is like prepaid. Then how do we construct the problem? So the problem is constructed like this. J equals to j in alt I xij prime. That's let me finish writing it and tell you. Xji prime. This equals to bi for any I. So let us interpret this. So according to the definition of the balance, that's to say, for all the node j that is alt I xij prime minus the inflow of I this equals to BI. So, well, I think the definition of balance in narrow flow problem is just the opposite of our understanding of money, because that's to say, the amount that you pay minus the amount that you earn, this is your balance. But I think in finance, in economy, we say that, oh, how much I earn minus how much I pay is my balance. In this way, if I earn more than what I pay, then my balance is positive, which is more reasonable, right? But keep in mind that in narrow flow problems, it is the opposite of finance. That's to say, your balance is how much you pay minus how much you earn. This is what the first equality tells us. And what is BI? Here it is a little bit tricky, because we know that in the original problem, we need every node to have inflow equals the outflow, right? This is what is stated in the original problem. So what should BI satisfy? Remember, keep in mind that in the original problem, you need to make sure that the income of I equals the payment of I. So now, in terms of the premium that I receives or I pays, the premium that I gives out minus the premium that I earns is BI. And we want to, and in the original problem, the amount that I earns equals the amount that I pays. So how to calculate BI? By some hint, the lower bound of the income arc and the lower bound of the outgoing arc. How can we calculate BI? Sean, do you have any idea? Remember, this is the premium, and this is the prepaid amount. Okay, so the BI, let me write it down. So it is sigma j in I, LJI minus sigma j in out I, Lij for any I. Okay, take some time to understand this. Why do I write BI be equal to LJI minus Lij? Why here it is in minus out? Oh,
If you plug it, since we've got the xij equals xij prime plus Lij, if you plug that into our original string over there and just move the Lij terms to the other side, we get that expression.
Yes, correct. So keep in mind that in the first equation, it is out minus in terms of the premium. And in the second term, as Thomas have suggested, you just rewrite this into Lij equals to xij minus xij prime, right? And then you plug back into the original problem. That's to say the inflow equals the outflow. Then you should be able to get this. So the balance of I is the LJI minus Lij. Keep in mind that this is very easy to make a mistake. So if you encounter this kind of problem in your exam, make sure that you get it correct, whether it is out minus in or in minus out. Think about it carefully. Okay, so and of course 0 is less than or equal to xij prime, less than or equal to uij minus Lij. That is the premium that you pay should be bounded by 0 and uij minus Lij. This is for any ij in A. Okay, and one more thing. We observe that sigma I in N BI, this equals to 0. My question is why? Why the summation of the balance equals to 0? Why the summation of the balance is just a 0? So refer to this equation. Why does the summation equals to 0? What will you get if you add all the BI up? What will happen?
They'll cancel each other.
Yes.
I mean, yeah, but I guess like say if you had like the node, like if you had node 1 and like I guess we'll just say node 1 and node 2.
Okay.
And that would be all the ins. Let's say all the ins of node 1. Yeah.
So this is just.
I mean, this is just an example. I know why. I just can't put it to words why, but basically like.
Okay, I understand what you mean. So actually, what I have explained is what is explained in the textbook. That's to say, for each arc, you take it twice. Because it is in minus out. So for when you are calculating B2, you plus L12, and when you are calculating B1 or B1, you minus L12, right? So that's to say for L12, it is included exactly two times in the summation of BI. When calculating 2, it is plus, and when calculating B1 is minus, then they cancel each other out. So finally, you get the summation of BI equals to 0. Okay, nice. Then, what is our task? Remember that we want to solve this circulation problem, stated here. Then, we need to check if this has a feasible solution. Then, to check if this has a feasible solution, remember, where are we now? We have S, we have T, we have some intermediate nodes, and we add one more arc from T to S. This is where we are now, and we have defined the flow ij prime. Say this is I, this is j, and it is xij prime. However, for each node, we introduced additional term bi, the balance of I. Then how can we check if this problem has a feasible solution? The idea is to add an additional source and sink, because we know that this is a circulation problem, not like a max flow problem. So what we do is to add additional source, additional sink. Well, actually adding additional source and additional sink is widely used in max flow problem. Remember that previously I told you, if you encounter a bipartite graph, what will you do? A common technique is to add S and T, and you solve a max flow problem, and you may get some very useful results for bipartite graphs. So for the circulation problem, you add additional node S prime and T prime. Then how can you connect this S prime, T prime to the nodes in this part? How can you connect them? So the way is it's like this. So let me write down. So the solution is that if BI is greater than 0, we add SI with capacity BI. And if BI is less than 0, then we add IT with capacity minus BI. What is the intuition behind it? So the intuition is like, I change to another color. intuition. So the intuition is like, because we know that when we are calculating generally in our flow problems, what is BI? The BI equals to total outflow of I minus the total inflow of I, right? This is for the balance. You pay how much you pay minus how much you earn. Then if BI is greater than 0, this is equivalent to I's out is greater than in, right? When I's out is greater than in, then I has a deficit. I has a deficit. So connect S prime and I to make in equals out, right? So this is just like when BI is greater than 0, it means that I's out is greater than in. Then I has a deficit. So how to make I's out equals to in? You connect S prime and I to make in equals to out. So remember that S prime is a supply node. So we can say that S prime, we make an analogy. S prime is like a philanthropy. If somebody is in a deficit, then he's in trouble. Then we use this philanthropy to donate some money to this guy, right? Then if BI is less than 0, what does it tell us? It tells us if BI is less than 0, then I's out is less than in. So I's money can increase, right? So to make a balance, T is like the government. They get more tax from those people, right? So because their out is less than in, so T is like getting more tax from these people, and S prime is like a philanthropy. It donates some money to those people who are in a deficit. Then we connect S prime and the nodes and T prime with the nodes in this way. So now what we are doing, we have already successfully eliminated the LIJs by introducing those BIs. And then to make this BI to be 0, we introduced S prime and T prime, right? Philanthropy and the tax office, or say the IRS. Then we can solve a max flow problem on this, because this is a standard max flow. This is a standard max flow problem. Balance equals to 0 and the lower bound equals to 0. This is what we favor, or what we favor. Then we solve a max flow problem. How can we determine if this has a feasible solution? If you apply the max flow algorithm onto this graph, and finally, for all the arcs that goes out of S prime, they are saturated. And for all the arcs that go into T prime, they are also saturated. Then this is a feasible solution. Otherwise, there's no feasible solution. So in this way, you find a feasible solution in this way. You find a feasible solution, and then you use the phase 2 that we have introduced, how to convert a feasible solution to a max feasible solution. Then this problem is done. So, okay, so that's all for today's contents. So if you have any questions, just ask. Then if you don't have any questions, then you're free to go. What is the time for the exam 2? 11:30?
I believe it starts when class starts.
11 o'clock to 12.